So this is our first video in a series of videos on how to receive, transmit, retransmit, and live broadcast radio signals. So the most simple out of all of these is receiving radio signals, and we're using FM radio signals because it's something that you can understand pretty easily. When you get into your car and you tune your radio to say 101.3, you're setting it to 101.3 megahertz, and the radio stations on that frequency you're listening to in your car. So it's something that everyone can kind of get a basic idea of, rather than some random signal at 5 gigahertz that might not be as clear. So this is Gnuradio Companion, and it's a flowchart tool that you use to actually build a Python script with these different blocks that will help you visualize and interpret the signals that you're getting through the HackRF. So when you open up a brand new file, it's going to look like this. You're going to have an options block, which just has an option for how you want to display your visualization blocks. The default is QTGY, and that is the one you want to keep it on because it is the most recent and has the most functionality out of all of them. And the other block you're going to have is a variable block with the ID samp_rate, and it's going to be set to 32,000. Now, first thing I want to do is set this up to 4 million, which you can do by typing 4E6 for scientific notation rather than typing out all those zeros. It will show up as 4M for 4 million, but you can't just type in 4M into it. It will not recognize that you mean 4 million. So the shorthanded way of writing it is in scientific notation. Typically, the HackRF can handle about anywhere from 1,000 samples per second to 20 million samples per second. 20 million is on the very high end, and you want a very dedicated computer if you're going to be running that high. You mostly do not need anything that high. Anything about 4 million or 2 million is usually okay for what you're doing. So our HackRF is plugged into the computer, and to actually take that and get the data from it, we need something that's called an Osmocom source. Now, to get this search menu up here, this menu is all your different blocks, and you could go through it and go for the different menus and look for it. But if you just click on the search button up here and type in what you want, it's a lot easier to find it, I found. So you can drag your Osmocom source into here, and it'll show you a bunch of different options. Now, to change these, all you have to do is either go to right click and then properties, or what I find easier is just double clicking on it, which will open up a menu. Now, some things you don't need to change at all. Number of motherboards, for example, is just how many HackRFs you have. We only have one, and we only need one channel at a time because we are just looking for one specific radio channel. Now, you can see that the sample rate is set to samp_rate. You can set these numbers as variable names, so that whenever I update this, say if I wanted to change it back to 2 million or something, it would also update in here, so you don't have to go through every single block that has a sample rate in it and change it. Up here, from where I am, the most prominent radio signal is 98.9, so we would just type in 98.9 E6 for 98.9 megahertz. And that's about all you need to do when it comes to this. Oh, and you want to change this channel 0 RF gain to 0. You don't need a decibel RF gain. It helps bring out the signals a bit, but it also in turn brings up some more noise, and it's not as necessary to bring it up in this specific example when we know what our radio station is at. Now it's all updated, and the next block we're going to put in is called a DC blocker, which is just a filter that it filters out the electronic signals that are going into the HackRF. If you don't have one of these, there's just going to be a peak at the very center of your graph. You're also going to set it to 1024, and no matter what, there's just going to be a peak, and all that is the DC voltage going into the HackRF itself. You don't need that because you can misinterpret it for a signal if you aren't careful about noticing where it is. So we can just filter it out entirely by setting this to 1024. Now to connect these together, all you have to do is click on the blue out on the Osmocom source and the blue in on the DC blocker, and it will connect them together. Now, if we want to look at these signals, we need a visualization tool. So the most easy one to use and the one that has the most functionality is a QTGUI sync. And this combines 4 different types of visualization into one block. And this one is useful because you don't really, if you need to change on the fly, you can have just this one rather than having 5 or 4 different blocks in your flow graph. So I like using this one the most. So we're going to connect those together. And we're going to change a couple things about it. We're going to set our center frequency to the same number as the one we set in the Osmocom source, so 98.9 E6. We're going to set our bandwidth to 20 million, so 20 E6. That'll show us hopefully the full length of the radio spectrum. And we're going to change our update rate to 5. The update rate is how many times per second the graph is updating. 5 is good because it's fast enough that you can notice it, but it's not straining your computer too hard. And we're going to change show RF frequency to yes, because if we don't set this, the bottom numbers will be set to 0 and then 5 million, 10 million, etc. And basically saying this is 5 million more than your center frequency. And we would rather have it say our center frequency is 98.9 million and show the actual frequencies of it rather than how much more it is. So now that this is a very basic flow graph, we can click play up here. And it's going to ask us to save our file. So we can just call it tutorial 1. And now every time we click play, it will auto-save the file for you. So it's going to generate the Python script down here. And eventually, it'll pop up with this, which is over on here. So we can bring this over here. And now you can see there's a bunch of different signals. There's one about at 104.3-ish. There's one that we're looking for at 98.9. There's one over here at about 91.9. And one here at about 100.9. So there's a bunch of different signals you can see. And the 98.9 one is the most prominent out of all of these. So if we take this back, the frequency display is the one in the QTGUI sync that we'll be using because it shows everything over, it shows the peaks over different frequencies. Now, if we want to actually listen to those files and to the radio station itself, we're going to need to set up a little bit more of it rather than just seeing the visual on its own. So the first thing we're going to do is put in a low pass filter, which will help us filter out everything that we don't want to hear, whether it be other radio stations or the noise that's below all of that. So dragging in a low pass filter, we're going to go from here to here. And some things we can change. We want to change the decimation to 20 because our audio rate is going to be 48,000 kilohertz, and we are currently at a sample rate of 4 million. So we're slowly going to move it down. So for decimating by 20, we are setting the sample rate to 200,000, which is not quite where we want to be, but it's the first step in getting there. Gain can stay the same. Our cutoff frequency, we're going to want to be 75,000. And this is basically how wide our filter is, well, or how wide what's not getting filtered out is. So it's going to be 75,000 kilohertz wide. And our transition width, we're going to set to 25,000. The transition width is basically how quickly you are changing from your filtered out to your not filtered out. So the lower your transition width is, the more sharp your transition is between unfiltered and filtered. So all of that is good. The next thing we need is something called a rational resampler. And what this does is this is changing our sample rate by a ratio. And the reason we need to do this is because if you try to just multiply or divide your sample rate, you couldn't say, I want to multiply my sample rate by 2.5. It has to be an integer. So you can use your rational resampler as a way of multiplying by a decimal, in theory, as a interpolation, which is increasing, over decimation, which is decreasing. And we want to set it to 12 interpolation over 5 decimation. And if you multiply our sample rate after the low pass, which was 200,000, by 12 over 5, it would be 480,000, which is close to where we want to be when we get to our audio rate. The next, after we connect these, the next thing we need is a WBFM receive, which is wideband frequency receive. And this is a way for us to actually get the audio signals out from the radio. Now, you're going to notice that this has an orange block on the side of it, whereas these have all had blues. Blue blocks coming out mean that the numbers that are coming out are complex, and that just means that they have a real number part and an imaginary number, say 3i, 5i, whatever it may be. There's 2 components to each of it. Normally, when you would convert from complex to float, which is orange, which is just one number, can be decimals or whatever, but it doesn't have 2 parts. When you convert from blue to orange, you usually get 2 outputs. One of them is the real counterpart of it, and one of them is the imaginary counterpart of it. The WBFM receive combines both of them and lets us listen to the radio station, because we do need both the real and the imaginary component to get the audio out of it. So we're going to connect these. And we're going to set our quadrature rate to 480,000, because that is the sample rate that is going into this block. And if we set the audio decimation to 10, we'll be at 48,000, which is what we want for our last block, which is an audio sync. Now, you'll see with our audio sync that it does have an orange input to it, so this is why we needed the WBFM receive. We can connect the audio sync, and we need to change the sample rate to 48 kilohertz, which is what is going into this. And that is what most stations play their audio rate as. Now, if we turn this on, we should be able to listen to it at 98.9. Now, because we're recording this entire screen, it is overloading and underloading a little bit, but in all, it is working. The audio would be coming through, and if we weren't recording the screen at this time, it would be coming through a lot clearer. You can, to try to take some strain off the HackRF, you can lower the sample rate, but to keep in mind, if you lower the sample rate, you need to basically fix all of this so that it still lines up to be 48,000. Ways of doing that are, if you cut the sample rate in half to 2 million, this would only be 1 million here. So you can set the decimation to 10. You could cut any decimation in half or double any interpolation, and it would fix your balance. And that's it for how to basically receive FM radio signals.